Welcome back. Today we're going to be looking at kind of what I would call the final iteration of Hack Week, Grow Week scripts. If you've spent any time with the original one we wrote, you know it works great up until you're at like 2 terabytes of RAM, at which point just hacking one server is not going to cut it. You got to expand, you got to hit more, but doing that requires a heck of a lot of effort. But this tutorial ought to walk you through exactly what needs to change. From the original script, I have made some modifications, and you'll have to pull these off the GitHub. Specifically, I've refactored 2 sections. Well, let's start with the easy stuff. I've added 3 functions. You just copy and paste these exactly as they are. Then I've refactored the actual batching algorithm. So we refactored into a calculate section, which does the math required to get the batch, and then it returns an object with threads, landing times, file names, and RAM requirements. And then I've refactored into a second section, which actually runs that proposed batch. This result here just gets passed straight into this function through batch. And you'll just have to trust me that it does functionally the same thing. It loops through the attackers, localizes grow threads to home, localizes the hack threads to a single server, and distributes the weak threads among any remaining servers. Then does a sanity check to make sure we actually completed the batch. And if it did complete, we exec it and we return available RAM to be used on the next target. So it's a little bit different, but writing that took, I knew it was going to take a while to refactor it, and I didn't want to waste a bunch of time on a video. Where it's going to get fun, though, is in these 2 sections here. Well, 3 sections here. So let's walk through what we've got now. We got a main script that gets the server list, same as we've been doing it, but in a slightly different format. Filters that 2 ways, targets and attackers. Creates an available RAM map and sets that RAM map with a key of the attacker ID, hostname, and the amount of RAM they have free. And it does that at the top of every loop. So at the top of every loop, it'll go back and it'll reset the RAM map. In fact, I should probably drop that into the loop too in case the available attackers changes. Okay, then for each target, we are going to calculate the hack percent that we want to use, and then calculate something I'm calling, well, actually not going to call it dollars per thread second, I'm going to call it dollars per RAM second. And this is the amount of money that we will make per RAM per second, per gigabyte RAM per second, by attacking this target. And it varies, and I can actually show you how it varies. Spoilers. Okay, I've created this script, test.js. All it does is exactly what we've been talking about before, and it goes through the targets and it calculates this value that I'm calling dollars per threads per second. And this is not the actual formula. I've modified it slightly since then, but the result is about the same. So note what it's doing here. It's sorting by growth, which was the original criteria we had in the first script. And then it's going to print out in order of growth from best growth to worst growth, this dptps value, which is going to be our new sort value. If I just run this, you'll see some interesting stuff, like Noodles was the highest growth, then Megacorp, being one of the highest leveled servers, is the second best growth. It's also got pretty good money per second, significantly better than Noodles. But where it gets really interesting is when you compare like Clark Inc. versus Fulcrum Tech. Those will be good ones to look at. So Clark Inc.'s dollars per second is 48.35, and Fulcrum Tech's is 221. But if we just run our list, you'll see that Clark Inc. is a 961 and Fulcrum Tech is a 951. So they're very similar levels, similar security levels over here on the right. So where's the discrepancy? Clark Inc. has over $500 billion max cash. Fulcrum Tech, 38.5. Likewise, the grow time of Fulcrum Tech, even though they're about the same level, and they both have, both are fully prepped, don't need any weakened threads, min security. The grow time of Fulcrum is twice as long as the grow time of Clark, and Clark's worth a heck of a lot more money. So between the two of these, you can just see straight up, Clark is by far a better target. So you can't sort by level, and you can't sort by growth, because if you look back at this, which is already sorted by growth descending, Fulcrum Tech has better growth than Clark. The difference is simply that Clark has a ton more money. So, since growth works by a percentage of total value on the server, growth is not the best metric to use, level is not the best metric to use, max money is not the best metric to use. The best metric to use is dollars per RAM per second. So let's write that function. And I'm just going to copy this to save us all some time. In fact, I'm probably not even going to put it here. This is what was in the old thread. But instead of sticking it just in this HWGW function, I'm going to create a new server object. Call it server.hwgw. And it'll import hackable base server and extend it. That way we'll have everything from hackable, as well as be able to add some new functionality to it, specifically expensive functionality that requires like nth growth analyze and so on. And that means I'll probably pull out some of this stuff from hackable, maybe not. We'll see. First, let's copy our update cache, because we're going to need this. Super. And I'll actually rename this to ID because that's what I've been using. Okay, so the super means inherit all the methods from earlier. And the update cache doesn't change, but we're going to create a new getter value. Here, we'll just start with that. We're going to call it, let's see what we got over here. I've got stuff like, is HWGW ready? I'm just going to go in and pull this out for sure. And I'll have is, let's keep it simple. Let's call it HWGW value. Yeah, it's fine. And this is going to be all that crap right there. So what are we doing here? We're getting what you might call the perfect batch. In fact, let's make that a function. So perfect batch will assume the server is at max money, min security, and it will return the perfect batch for that server at that time. And it'll just do threads. That's all I'm concerned about. So hack threads will be that. Week 1. I'm still going to have to modify this, but it'll come in handy to do it like this, and you'll see why later. Because this is a getter, it can be cached. All right, so HWGW value is going to be start with return dollars divided by RAM per second. And then, yep, let dollars equal hack percent times target money max. And we will just set, I'm thinking, how are we going to do this? Can we do like calculate hack percent? And for now, we'll just return 0.1. Right now, calculate hack percent's in the other script, in this guy, but I'm going to take it out and just do it over here on the new server type. So we'll return this dot calculate times target money max divided by RAM's going to equal perfect batch hack times 1.75, and then we'll just add up all of our different types. So the other types are 1.8 gigs per script. And that's the RAM that's required to achieve a perfect batch. And seconds is just going to be times 4.0. I'm not going to add in the extra buffer. And that'll do it. That will get a dollars per thread second value. And I said I had to come up here and fix perfect batch because, for one, this is going to be, in both cases, this .ns. Now that we're referring to the server itself, okay, home.cores is going to be interesting. I think I'm going to not make that a getter because I'm probably going to need to pass in some arguments at some point. Like, for example, an attacker's array. I don't know what it's going to look like, but for now we're just going to leave that as a method. Okay, so this num cycle, that's definitely going to come over here and become probably a getter function. No, it can't be a getter because it's got parameters. No big deal. And I was thinking that maybe I could modify server, but I'm not even going to mess with it. Come back and do that later, clean it up a bit. And last but not least, home. Home is going to be a new. There we go. That's all we need to get cores is hackable base server. No reason to complicate it. And then we've got home cores. I probably want to do this a little bit different. So that I can later refer to them when I'm in the week 1 and week 2, just below, because you can't self-refer to an object. But you can do it like that. Okay, so we got all the way through, and this should be a value that is on the HWGW server at this point. We'll come back and we'll change this from a hackable base server to an HWGW. Yeah, I'm going to have to split this out a little bit different. I'm just going to delete this, do that over. Do it exactly how it was in the other one. Perfect. And then we'll export as the default. Okay, I think I'm good here. Next up. We're going to sort, instead of sorting by growth, by this value that we just created, HWGW underscore value. And then we're going to split into ready targets, which are targets that are perfect, and unready targets, which are targets that are anything but perfect. Then we've got this required ready targets. So the importance of this is we don't want to ready too many targets, and we also don't want to ready to not have enough targets to maximize our RAM. So we'll have to calculate that. But for now, let's just keep running through it. If ready targets length is greater than required, so if we have enough targets, then we enter HWGW stage, which means we loop through the ready targets and we calculate the batch, which is this nonsense, and then run the batch, which is the exec section of it. And if we don't have enough targets, then we will prepare more targets. So we'll let target of unready target and do something. So these two pieces are going to go hand in hand. How are we going to do that? Well, let me pull up the code I've already written, because I figured this out and it took like 2 hours and I didn't want the video to go on that long. But likewise, the code is probably a good bit too complicated just to post without explaining it. Like I can do that with the calculate batch because it's pretty self-explanatory. Like you read through this and you'll know what it does. Maybe you don't know what this does, but you'll figure it out. But this is really complicated. So, let required ready targets equal. Okay, this is a reduce. Hopefully by now you know what a reduce does. It takes an accumulator and a target, and for every time through the loop, it passes the accumulator back into it as accumulator. So it becomes, it's literally an accumulator. It will be available in every loop, and you can add to it, subtract to it, call it an array and push to it. You can do anything you want with it. It just is a value that is present in every loop. And target is the current loop. So sometimes you see this as like accumulator and current. So like target.reduce, on the first time through, target will be the first index of targets. And on the second time through, it'll be the next target and the next target and the next target. But accumulator is going to be passed over and over and over as is. It won't change unless we change it. And reduce also takes one other variable here. Usually people set it to 0. That's the starting value for the accumulator. But I'm actually going to set it to an array of value So this is a function that will reduce the attacker's array in a way that sums up their total max RAM. So if you think about it like accumulator, what this does, when it starts on the first loop, it will start as this value, an array with one entry, which is the sum of the RAM available total. Okay, let's work from there. What are we going to do to the accumulator? Well, you always have to return the accumulator. And then before we return it, we're going to modify it. And we're going to modify it like this. And I'll explain what this does in just a second. So what we want to do is calculate the number of targets that we can afford RAM-wise to attack. Like we want to max out our RAM, so the number of targets will be exactly equal to how many servers can we attack simultaneously, right? That's just the logical way. When you start coding, you always start from clearly stating what problem you want to solve. And the problem I want to solve is calculating the number of servers that will fit in the amount of RAM I have. So I'm using RAM required. Now I have to figure out what the required RAM for any given server is. But after I get that, how I'm structuring it, and remember, this is what I'm trying to clarify here is the difference between your data structure and your algorithm. The data structure is an array that gets pushed to with RAM required or some other value. And the reason why I'm structuring it like that is because I'm actually going to set required ready targets to whatever this reduce function returns, dot length. So it's going to yield an integer because accumulator is just going to keep pushing values onto this array. And I don't really care what the values are. I just care how many there were. And so the length will be the total number of values that we could fit in. And that way, ready targets.length and required ready targets will be comparable integers. And as far as this deciding whether or not to push a value to the accumulator, that's as simple as if the required RAM is less than or equal to the most recent RAM that we posted. That's why we're doing it with RAM required and pushing that, because we're going to compare on the first iteration through the RAM required for target 0 and see if it's less than the most recent, which would be the only value in there, the total amount of RAM. So if the RAM required is less than or equal to the total amount of RAM, we're going to push a new value onto the stack. That will be that, I believe. The accumulator's most recent value, same as this, minus the RAM required. So we're descending this. So think of it, that didn't make any sense. Got 1,000 RAM required. First target takes 100. Second target takes another 100. Third target takes 300. So we're just counting this down until RAM required is bigger than that last number. And then we say no more. That's how many targets we can fit. Okay, so how are we going to get RAM required? Well, I think we just wrote that function. That's the RAM required for a perfect batch. But that's only one batch, right? That doesn't take into account that one target can be hit with multiple batches. So we'll call that batch RAM. RAM required is going to be equal to batch RAM times simultaneous. How are we going to get simultaneous batches? The easy way, or the way that I thought, is we know what our timing is. Our timing is 160 milliseconds per batch. And that means if we take the hack time of the target, multiply it by 4 to get the weaken time, and divide it by 160, we're essentially getting the number of batches that will fit inside the weak time. So if the weak time is 2 minutes, that means a batch is going to fire at, well, that means a batch that fires at 2 minutes will be free at 4 minutes, and one that fires at 4 minutes will be free at 6 minutes. But we can stuff batches every 160 milliseconds in between 2 and 4. Likewise, if it takes 5 minutes to weaken it, we get 5 full minutes of 160 millisecond batches that we can stuff into that 5 minutes. And how many 160 units can you stuff into 5? That many. The minimum required ready targets is going to be the batch RAM times simultaneous batches. Specifically, if that number is less than the amount of RAM we have after considering every previous target, ready target, or just target. Doesn't matter if they're ready or not. So that way, if we've got 5 ready targets, but we want 6, we won't go and ready 6 more targets, we'll go and ready 1. Yeah, I think that'll work. And then kind of the other half of that is this. What do we want to do when it's time to prepare more ready targets? Well, you'll see in this calculate function, I've got this prep batch. Its default is false. It's not going to be a prep batch by default, but if we want it to be a prep batch, what does that change? Well, prep batch, if prep batch is true, there won't be a hack percent, there won't be hack threads, and there won't be grow threads as a result of the hack. So all we have to do to get our prep batch is be like, let's propose, same as we did before. Calculate the batch for target with the parameter true. And then we just run it. NS attackers target propose batch. I may have to do something with this available RAM number. Yeah, I think I am, because I'm returning available RAM down here. But what's interesting is, so top line notes, passing it in, cloning it into RAM map, and then I'm reducing the available RAM, storing it back in RAM map, but then I only pass RAM map back up if we could execute it. So if we go through all this stuff and realize, hey, wait, we actually don't have enough weak threads, it won't assume that the RAM is lower just because we were setting it down in this function. It's going to wait until we pass it back after an exec. What that means, you have to store it. Probably want to store it here too. And I'm thinking we just do something like, if it got stored, because if it doesn't get stored, it's going to be a null and this will resolve false. So if nothing happened in the batch, this will never run. We'll store it back in available RAM. And then we're going to have to do, well, let's go on and copy this. Put it up here too. We're going to have to do something that says sleep for some amount of time, because as it is, these targets will still be unready after 160 milliseconds. It'll loop back through and it'll say, oops, I found unready targets. Let's target those again and try to ready them. So I'm just going to set a hard and fast rule that if we get a result back, if the batch ran, let's create an array, call it prep times, and we'll push to that array something. And then we'll sleep for whatever time. Let's do it like this. If we have anything in prep times. Then we will sort such that the longest time is in the first slot. And then we will sleep for the longest time. So once we come through this and we realize we need to prep more targets, we'll go start prepping that target, and then we'll just go to sleep until that target's prepped. And that won't be perfectly efficient. Like, it might be the case that we need at some point like one more target because we increased RAM on a home, but we don't want to stop running our general batch script. But it'll be good enough. In the vast majority of cases, most or all of your prep needs will fire the first time you run the Hack Week Grow Week script. And it'll sleep until they're done, or at least you'll fill up your RAM every time. And then if you need more targets, you'll probably fill up your RAM again. Worst case scenario, this is like a one-time loss. And we don't try to optimize one-time losses. You try to optimize losses that happen every cycle, but you don't worry about the one-time stuff. So what are we pushing? We're pushing a time. And I know in proposed batch, I have landing times. It'll be the week 2 landing time. But this is a performance now number. So it's a time stamp, a number of milliseconds. We don't want to sleep the whole number of milliseconds. We want to sleep the number of milliseconds when it lands minus the current time. And we probably want to floor that. Actually, let's seal it. What's another millisecond? Might save us from trying to run a script half a millisecond too early when we don't have the RAM available. Okay, so prepping the ready targets, we're setting up the array, we're running through the list of unreadies, getting the batch, running the batch, checking if the batch worked, pushing the requested sleep time, and then every time a target runs through, if it executes, we'll push to the sleep time. Then after the loop is done, so you look at that bug I fixed just by walking through it. Always walk through your code. After the loop is done, if there's anything in prep times, sort it from longest to shortest, and then sleep for the longest. I probably need sleep here too. I don't think I need to sleep here, because that sleep is technically happening down here. The only reason I'm adding a sleep here is because you can afford to space out. Like I said, you don't try to optimize your one-time things, and prepping targets is a one-time thing. So you add an extra sleep just to be safe, make sure it runs okay. But this, I'm not going to add it unless I need it. Okay, what else we got? One thing before we paste this into the game and run it. Since we added all this stuff to the HWGW, specifically we added perfect batch. I'm wondering if we shouldn't slightly refactor this. So hack percentage. We don't want to have two sources of truth for hack percentage, and we are doing it in both spots. Why are we doing it here again? Because we have to have it for perfect batch. So why are we doing it over here? Yeah, I like that better. We don't actually even need it because we're not going to use hack percent anymore once we just say target.perfectbatch. Does that work? Yeah, it ought to. And then the week we'll do perfect batch. So this is already a number of threads, and this piece is creating a number of threads. So this is the fixer component. If the security level is, if it gets off at any point, this will attempt to fix it. Not super efficient, but it very rarely gets off, and this saves you a bunch of problems. And then grow threads. That's our target perfect batch grow. And that's our week 2. Beautiful. If I used calculate hack anywhere else, I didn't. Good. All right. Have we done everything? I think we're ready to run it and just see what happens. Let's pop over to game. Slap that in there. And we need our server object. I don't know if it's going to work or not. I probably forgot something. Oh. Yep. We can import both of them. It won't hurt anything. Or you can change all the homes where it sets, well, actually this right here needs to change as well, but I was thinking it was where we go out and like hard set the home value. NS is not defined in perfect batch. Constants is not defined. Okay. That'll be out of server hackable. Probably just move all this crap over all at once. Not even worry about it again. Well, it's running. And it's just sleeping. If we can figure out why. First off, I'm going to check the new functionality I made. Let's see how many required ready targets it thinks we need. 11. That checks out. We've got a ton of RAM. Let's go in and check ready targets.length. I don't think it's going to be a bug here, but yeah, we got 37 ready. My guess is the bug is going to be somewhere, whoops, down here with the batcher. We'll check our sanity checks. False, true, true. Okay, so the weak sanity check is failing. We'll print out the entire batch. See why. Oof, shit. Okay, so that's a batch. The attacker noodles, weakening with 2 threads. Food and stuff hacking with 8 threads. Food and stuff weakening with 1 thread. And max hardware weakening with 1 thread. And home growing with 40. Okay, well, we know this divided by 25 equals the weak threads. That would be 2. We've got one with 2. Yeah, this shouldn't be breaking. I'm missing something else. See what happens if I do that. Yeah, something's causing my weak sanity check to fail. So the weak file name, that's correct. Weak threads is equal to batch threads week 2 and week 1. Maybe it has to do with this perfect batch. So grow threads over 12.5. I mean, maybe I'll start by just printing out perfect batch. Where are we going to do that? About right here. Okay, well, we're getting numbers. So there's something in it. Ah. That'll do it. And there we go. Now everything fired off. and we have extreme lag. We're not frozen, there's no infinite loops. But significant lag. We'll check the inspect. Sometimes it'll tell you what's going on. There'll be errors getting thrown like crazy, but I think I suspect what the problem is. Reduce operations are really expensive. Yeah, no errors coming out. And then it frees right back up. So it's definitely that reduce that is killing us. I bet I can prove it too if I head back up and just comment out that right there and say let required ready targets. Just set that to 11. I imagine no lag at all. Let me take out that while we're at it. No, we're still lagging. Pretty bad too. So something else is going on. The thing is, I know this half of the loop isn't running because we don't, like, we have enough targets. So it shouldn't even be anything in that. And the only other thing I changed was this. So what is going on with the calculate batch? Could there be an infinite loop in it? I don't think so. I don't think I have any loops. So no loops in that. So it can't be that. And the run batch. We have attackers for each. And then we're just doing really, really simple calculations. I suppose this, anytime you got a reduce, that's the first place I look. I don't think that's going to cause it. Could be the exec if it's trying to exec a ton of threads, but I doubt it. Maybe I do need a sleep here. Let's try putting one in just and see what happens, because well, that seems to have fixed it. Oh yeah, we're good now. So maybe that lag was temporary because home has so much RAM, it was like trying to calculate tons and tons and tons of threads all at once, literally all in the same millisecond. And you just give it a little bit of space and your usability goes way up. But does it actually fill up? Well, it's doing more than it was. It's got freaking 4,000 threads running and it's not full. We're not 4,000 threads, 4,000 scripts. Yeah, so the other half of this is that calculate hack percentage. Because if you up the hack percentage, your RAM requirements will go up, but your money will go up, but it'll go up exponentially. So like adding every dollar you add or every percentage you add to hack percent raises the RAM cost by n to the power of something. So it's not as easy as just calculating your RAM cost or calculating your ideal number of percentage of hack. In fact, I'm probably going to leave it like this just because I've got 256 terabytes, man, and it's still half full. But if you wanted to take a crack at calculating the hack cost, knock yourself out. It looks like it's filling up even still, so it may continue to go up. You would think that, like, it said there were 11 targets, right? It said it needs 11 ready targets. We had 37. So you would think it would go on and continue filling up until it hit that 11, or else maybe the calculation for how many ready targets we need is wrong. All I know is this is filling up pretty good for now, and we're coming up on an hour with the video. So are we going to revisit this later and look at calculate? I don't know. Maybe I'll leave that for you to figure out, and I will stick with what I've got now. All right, thanks for watching. Come back next time. We'll see you on source file 4. It may be a couple weeks before I get there. If you're just starting out and you haven't done anything, I strongly recommend doing bitnode 8. That takes about a week to finish, but not with the scripts we released for the stock market just the other day. Check those scripts out. You'll breeze through bitnode 8. And then we'll catch you back on 4. All right, thanks for watching.